So diode operating condition. Diode can operate in 3 different conditions: no bias, forward bias, reverse bias. You got in low. You kind of already know forward bias and reverse bias. No bias means just basically nothing. Okay. Also, um, biasing. What does bias means? Bias just basically means you have some component. Okay, you have some component, and you're applying uh, a power supply to it. So say plus and minus. This is just called biasing. Okay, that's what it means. If I have just component, okay, and it's not connected to any power supply, uh, it's just a component. There's no bias here. Okay, no bias here. Okay, so it's something that is related to the power supply. So just keep that in mind. Now, no biasing, basically you don't have no external voltage is applied, right? So if nothing is applied, voltage of the diode, VD is the voltage of the diode. If voltage is 0, you know current is going to be 0. Only a modest depletion region that exists. So it's not that depletion region is not going to exist. It's going to be there, but it's going to be modest, not too big, not too small. Okay, so that's one of the operating condition. Um, the second is the reverse bias, correct? Reverse bias, remember we reverse the polarity, right? So you have negative terminal is connected to the positive terminal of the diode, and the negative terminal of the diode is connected to the positive terminal of the diode, okay? And in this case, what happens? Let's see this graphic, and it's important to realize this. Okay, you have a p-type material and you have an n-type material. So this is p-type and this is n-type. This is the positive terminal of the diode and this is the negative terminal of the diode. I have the negative terminal here, okay, connected to the positive terminal over here of the diode. So is that going to be reverse bias or forward bias? It's going to be reverse bias because I have the uh, power supply just swapped, okay? It's a reverse polarity. And then also because in a reverse bias situation, the depletion region, the length of the depletion region is going to be very large, okay? Again, you think of depletion region as resistance, and because the depletion region is high, resistance is going to be high. Because resistance is high, there's no current going to flow, so there's no current, okay? So I majority is basically the current, and the flow of the current, we know that the current flow is from, the conventional current flow is from positive to negative terminal, right? Conventional current flow. So you have the positive terminal of the battery, you got a negative terminal, so it's gonna go like this, like this, like this, and then come back. But the current is going to be 0 in K because the depletion region. Now, ideally you think it's 0, but in reality it's very, very small, very, very like few microamps, okay? Because even though it has some high resistance, but some majority carriers over here might still be able to go past this depletion region. So again, this is going to be a very, very small number. So the reverse voltage causes the depletion region to widen. So just remember that reverse voltage causes the depletion region to widen, which means that there's an increase in the resistance. The electrons in the n-type material are attracted toward the positive terminal of the voltage source, and the holes in the p-type material are attracted towards the negative terminal of the voltage source, kind of like what we discussed earlier also. The third part, which the third operating condition is the forward bias condition, which I told you the positive terminal of the power supply connects with the positive terminal of the uh, diode, and the negative terminal connects with the negative terminal of the diode. This is when depletion region actually decreases, and that's what you see over here. The depletion region is very, very small. So if you look at here, again, this is the p-type material on the left, okay? And this is the n-type material on the right. You got positive here, so you got positive charges going in here, correct? Positive charges going in here. This is a p-type material. P-type material, majority carriers are plus, right? Majority carriers are holes which carry positive charge. Because you have at the input terminal, you got positive. These positive charge are going to repel. So all these positive charges are going to have some extreme amount of pressure that is going to pull these charges to the right, correct? And then they come out, get attracted towards the negative terminal of the battery. So the electron flow is going to be like this, okay? And that's where you see this sign right here. This is the I majority, okay? What is this S right here? IS is basically the short circuit current. Like I was saying, there will be some amount of current which will flow in this direction. It's going to be very, very small. It's almost negligible. Um, and we call it IS. And like I said, it's going to be very small. Majority is the current that is flowing from left to the right, okay? So what do we learn here? Well, in forward bias, the depletion region becomes narrow. Okay, narrow means very less resistance, so electrons will flow. The electrons and holes are pushed towards the p-n junction. The electrons and holes have sufficient energy to cross the p-n junction. Okay, remember, uh, if you look at this over here, because the depletion region is very small, okay, but still not all of the holes will be able to go past over here to the right hand side, okay. Only those carriers which have enough energy, enough to go past this depletion region will go, and most of them will go because they are connected to the positive terminal of the battery, which is a high pressure compared to what is over here on the right, okay. Okay, now actual diode characteristics. So we were discussing earlier that the characteristics of the diodes are such that the current will flow right away when in the forward bias region, and then the current will stop flowing in the reverse bias region, and if there's a no bias region, basically that means nothing, okay. So I want you to focus over here, okay, where on the y-axis you got the diode current, y-axis, okay. And on the x-axis, you got VD, which is the diode voltage. So this right here, when VD is 0, which means no external voltage is applied. When VD is 0, ID is 0. So that's your no bias here, correct? That's your no bias. Okay, now look at over here. I want you to focus on this region right here, okay? This region right here. This region right here is actually when VD is in positive, right? VD is in positive, so some positive voltage is applied. What would happen when a positive voltage is applied across the diode? What should happen to the current? The current should, yes folks. So again, I want you to focus here to the x-axis, okay? To the x-axis over here. As the voltage applies, the current should go up like this, slowly and slowly, correct? Right? That's what you would hope, right? That is actually not happens. What happens is because your diode is made up of a semiconductor material, so say it is made of germanium, okay? Germanium has a potential drop of 0.3 volts. What does that mean? So say at the input you are getting 5 volts, at the output you will get 5 minus 0.3, 4.7 volts, okay? Similarly, if you have a silicon diode and at the input you got 5 volts, the potential drop for silicon is 0.7. So at the output V naught, you will get 5 minus 0.7, which is going to be 4.3 volts. Okay, so what I'm trying to say, diode does not conduct electricity depending upon what kind of material it was used. So I'll look at this black dotted line and I'll try to just, so it'll be 0, okay, your current will be 0, but once the voltage drop reaches 0.3, you'll see it'll start going up. It'll start going up like this. And it'll just go up, shoot up. Okay, all right. So this black line that you see, which I just overlap with the red one, does it tell you that this diode was made up of germanium or silicon? Yes, folks. What does it tell you?
Germanium.
Germanium, yeah, because germanium has a voltage drop of 0.3, so it will wait for the voltage to get to 0.3, and that's when the electrons will kick in and start flowing. Okay, but if you look at the other one, blue, it has a very, very small current, you know, and then just around 0.7, which is this right here, it kicks off. Okay, so something like this. Okay, so that means this is for the germanium, the black one, and the green one is basically for the silicon. Okay, and in this region, basically your this whole region right here, okay, your diode is working in what region? Forward bias, reverse bias, or no bias? That's the forward bias, right? And what happens in forward bias? Forward bias, your diode conducts, right? Your ID, uh, uh, ID goes up. Okay. Now let's move on to this part of the graph. Okay. So what is happening here? Negative voltage is applied. Okay. Negative voltage is applied. You got negative 10 volts, negative 20 volts, negative 30 volts, negative 40 volts, right? When you have a negative voltage applies, what happens to the diode? Diode will not conduct electricity. So your current will be 0. But in actual diode, it's not 0, but it's very close to 0. So you see, it's negative 0.1 microamps. It's very, very small, very, very small. Okay, and that's what we refer to as a reverse bias condition. Okay, right. Um, so very, very basics of a diode right here. Anyone has any question before I moved on to the transistors now? This was the diode. Maybe, you know, I can also give you, let's see. Yeah, let's do over here. So say I have a circuit. I have a circuit and I have a diode here. Okay. I say this is silicon diode, made up of silicon, and then I have the load over here. And then this is the RL, okay, and voltage across this is some voltage VL, okay, and then at the input I got something like this, okay, this is my input, say VN, okay. This input voltage will go past silicon, right, diode. So how my output will look like, say on the x-axis you got time, and this is your VL, right? Whatever the voltage is over here is the voltage across this resistor RL, but I'm interested in what is the voltage over here. Okay, now, so say I start from here. Maybe I can change the color here. During this time, say the peak voltage is 5 volt, and similarly, this is the negative fuse will be negative 5 volts. So during this positive half wave, the values are going to be positive or negative for the Vn. Yes, folks. It will be positive values, right? So say maybe this may be 1 volt, 2 volts here, 5 volts here, 3 volts here, 2 volts here, 1 volt, 0 volts here, correct? All these values are positive. So that means if you have a positive value here, this positive terminal is connected to the positive terminal of the diode, In the negative terminal, you got this. So is your diode working in forward bias or reverse bias here? Yes, folks.
Forward bias.
Forward bias, it's working in forward bias. So your output voltage VL is going to be similar to what you have over here at the input, right? It will be like this, correct? However, the magnitude is going to be what? What about the magnitude? Because you get 5 volt here, peak value, this peak value, V peak is 5 volt, and but you have silicon here. You know, silicon voltage drop is how much? 0.7 volt. So this peak value is going to be 5 minus 0.7, which is going to be 4.3 volt, correct? Right? Okay. Now, what happens to this part of the input signal? All these values are negative here, correct? In the negative half wave. All these values are negative. So I'll have a negative number here, negative number here, negative number here, which would mean the polarities are going to change here. So I would have negative here and then positive here. When I have a negative terminal connected to the positive terminal of the diode works in a which region? Forward bias, reverse bias, what? Yes, folks. It's going to work in reverse bias, correct? Right? That's what we learned here. Reverse bias, when we have the opposite polarity, no current flows. Majority is 0, correct? So no current flows. If the current is 0, you apply Ohm's law. If I is 0, then you get 0 volt here, right? So you'll basically get 0 here. And similarly, again, for the next cycle, you'll get some voltage here, and then you get 0 here, and then you get a voltage here. So for the positive half wave, you get all this, right? And for the negative half wave, you get 0 here, right? So in a lot of applications, you need something like this, okay? Like it's kind of like a on and off thing. This time is on, this time is off, this time is on. If you can set this time period that for 1 second it's on, 1 second it's off, you can actually sort of kind of make like a digital circuit on that. So that's one of the application of the diode. This process is known as the half rectification, okay? Half rectification. And this circuit that I just drew here is a half rectifier circuit. Circuit, okay? So clipping off the negative, this is clipping off the negative, input signal, and just keeping the positive signal. So this is a very simple example or application of the diodes.